Welcome back to these videos here. Today we'll see an example, or several examples rather, of how to actually compute an inverse matrix. We'll start with a very concrete one. So here's a matrix A. I'll make it a 3 by 3 matrix to not make things too easy. Let's say this is the matrix that we have. So row by row, this is 1, minus 1, 4, 0, 2, minus 1, and 1, minus 2, 4. We want to compute the inverse matrix of that one if it exists. And what we are going to do is we're going to employ the procedure that we have seen in one of the previous videos. And that works by writing this matrix here as the left-hand side of a tableau, like this. So here we have that matrix. On the right-hand side, we'll start with the identity matrix. So this is I3. And then we're going to use row operations, elementary row operations, as in Gaussian elimination, to compute echelon form for the left-hand side. Now what we need to do here is, first we'll use this here as our first pivot element. And we need to make zeros here in these entries. There's a 0 here already, so nothing to do for row 2. And here we can just subtract row 1 from row 3 to get a 0 in that position as well. So first step that we're going to do is we're going to subtract row 1 from row 3. Let's just copy the first row. Also here on the right-hand side, of course. We don't touch the second row, so we can copy that one as well. And for the third row, we get 1 minus 1 here. We get minus 2 plus 1, that's a minus 1 here. And we get 4 minus 4, that's a 0. For the right-hand side, we have 0 minus 1, that's a minus 1. 0 minus 0, and there's a 1 minus 0. So that's how this will look. And you'll see we already have our first pivot element and our first 0 column below that pivot element. Now, looking closely at the second column here, we can see that here's a minus 1 and a 0 here. So it might be nice to actually move this row up here, because it will make our computations a little easier. We could also do this in other ways, of course, but I'll decide to do that. So we just swap those last 2 rows here. And we get, first row is just being copied. The new second row is the former third row. So we have 0, minus 1, 0, and then minus 1, 0, 1. And the new third row is the former second row. So that is 0, 2, minus 1, and 0, 1, 0. Okay, going on with the computations. We take this as the next pivot element and use it to obtain a 0 in this position. And to do so, we just add the second row twice to the third row. So here, plus 2 times the second row. And while we're at it, let's multiply that second row by minus 1 so that we can obtain a plus 1 here. That's what we'll need in the end anyway, and it just makes for a nicer look right now. Okay, the first row is just being copied once again. the second row is being multiplied by -1. So here's 0 plus 1, 0. And the right-hand side becomes 1, 0, -1. And the third row, when the 0 here stays, here we get 2 minus 2, that's 0. -1 plus 0, that's -1 again. On the right-hand side, we have 0 minus 2, 1 plus 0, and 0 plus 2. So that's -2, 1, -2. And it's at this point that you can see here we have these 3 pivot elements, and we have a matrix in echelon form. So from this we can conclude that the rank of A actually is 3, and that means there is an inverse. A is invertible. So we can continue with the procedure. And that means we now have to obtain reduced row echelon form. So we kind of restart the Gaussian elimination procedure, now going back from the right bottom corner. So we'll use this pivot element here to obtain zeros above the pivot. The second row is fine already. That first row here needs to be dealt with. What we can do here is we just can add 4 times that third row here. And again, there's a -1 here. We want a +1 in the end. So let's multiply this by -1 while we're at it. Now what do we get? This time we do modify the first row, so don't copy that. On the left-hand side, that's easy because there's zeros here, so nothing happens to those first entries. That's 1, -1. And here we get 4 minus 4. So that's a 0. That was the intention all the way. So what happens on the right-hand side? So here we have a 1, and we add -2 times 4, so we add -8. That's a -7. Here we have 0, and we add 4 times 1, so that's a 4. And finally, here's another 0, and we add 4 times 2, so that's an 8. That's our new first row. The second row doesn't change, so we can copy that. And the third row, we multiply that by -1, so we get 0, 0, 1, 2, -1, -2. So that's our new system here. And there's only one thing left to do. As you can see, this pivot here is fine. It has zeros above. There's no below, so that also is okay. This pivot here has zeros below, but not yet above. So we need to take care of this entry. And we can do this by just adding the second row to the first one once. So let's do that. What we get is 1, 0, 0. And on the right-hand side, we will get -6. 4 plus 0, that's 4. And 8 minus 1 is 7. And we just copy the second row and also the third row. And now you can see on the left-hand side, we have actually obtained reduced echelon form. In other words, the left-hand side is now an identity matrix. And that means the right-hand side, this matrix here, that is now the inverse that we were looking for. So the inverse of A is the matrix -6, 4, 7, 1, 0, -1, 2, -1, -2. And of course, it might be a good idea to actually verify that this is correct. So I'll invite you all to pause this video for a few minutes and see if you can compute the matrix products of A and this inverse here to see if that actually yields the identity matrix. Now, welcome back to our second example. This is going to be a little more abstract, but it's also going to yield a useful formula. We are now going to look at a 2x2 matrix. That's a pretty easy case. So for 2x2 matrices, we just have a look at the general case. So the general 2x2 matrix will look like this. A11, A12, A21, A22. And we want to compute the inverse of that matrix. Now, how do we do that? Well, just use that procedure on the general entries here. So we write that matrix as the left part of a tableau, and we write the identity matrix as the right part of a tableau. And then we can try and perform Gaussian elimination on the left-hand side here. And the first thing that we can do is, to make things a little easier, let's multiply that last line by A11. And of course, that only works if A11 is not equal to 0. So we'll have to deal with that case separately later on. Otherwise, that last line would just vanish. Yeah, we would lose the information in the last line, and we don't want that, of course. Yeah, so don't multiply by 0. You can multiply by any non-zero elements, though. So what that gives us is, well, the first row is not altered in any way. The second row is now A11, A21, and A11, A22. And on the right-hand side, we get 0 and A11. And now what we do next is we subtract A21 times the first row from the second, because that will give us exactly this coefficient here to produce a 0 here. Now if we do this, what we get is an A11 here, a 0 here. That was the intention. The A12 here is not changed. The expression here in that position, that becomes a little complicated. So what we get here is A11, A22 minus A12, A21. That doesn't look too beautiful actually, but yeah, we can deal with that. First row is not changed here. Second row is now minus A21, A11. Now to be able to make the notation a little more concise, we'll use an abbreviation for this here. We just call that D. And what we need to do next is we'll make sure that D is not 0. If D is 0, then the matrix doesn't have full rank, obviously. And if that is the case, then we can stop right here, because that means the matrix is not invertible. So it's important that this is not 0. Otherwise, the rank of A is less than 2, and we can stop right here. So that's an easy way to check whether a 2x2 matrix is actually invertible. Just compute that expression, that D here, and see if that is 0 or not. Now if it's not 0, we can go on, and we want to have a 0 here. So basically we need to subtract A12 over D times the second row from the first one. And that's how we get A11 and 0 here. We get 0 and D here. And on the right hand side, what happens here is a little more complicated, unfortunately. So we have minus A12 over D times this expression plus 1. And now that yields, so 1 is obviously D over D. So we have D over D. And we subtract minus A12 times minus A21. So that means we add A12 times A21 over D. So this is the result in this position here. We have a 0 here, so that's a little easier to compute. We just need to multiply A11 with that expression here to get the result here. So we have minus A11, A12 over D. And then the second row is not altered in any way, so we have minus A21 and A11. And finally, two things we need to make to obtain our final result is we need to multiply this by 1 over A11. And remember, A11 was not 0. We said that before. And we have to multiply this by 1 over D. And remember again, D is not 0 as well. And now, well, what do? Do we obtain? The left-hand side here is as desired, the identity matrix. The right-hand side, what happens on the right-hand side? Well, that's a little more complicated, but not that bad actually. So remember D was, you can see that here, D was A11, A22 minus A12, A21. And what happens here is we add A12, A21, that's just this expression. So minus this expression plus this expression, that cancels out. What's left is this term here. Okay? And then we divide that by A11. So this term divided by A11, well, obviously, that's just A22. And of course, this over D, that's also left. Yeah, that stays. So what we get here is A22 over D. Here, we just divide by A11, so what's left is this part here. So here we have minus A12 over D. And down here we have minus A21 over D. And A11 over D. So that is our inverse. And what that means is A to the minus 1, we can just take out this 1 over D, then the formula gets to look a little nicer. So this is 1 over D times A22 minus A12 minus A21 A11. With, again, D is equal to A11 A22 minus A12 A21. Now, of course, we still have to make the computations for A11 equals 0. But I'm going to spare you that. I'm going to tell you right away that if we do this, the outcome is exactly the same. So you get the same outcome for A11 equals 0 and D is not. So we established before, if D is 0, then the matrix is not invertible, and that's also the case for A11 equals 0. So what does it give us? Well, it gives us a nice formula for the inverse of a 2 by 2 matrix. So basically what you have to do is for a 2 by 2 matrix, you calculate that D, that's probably the most complicated part here. And then for the entries on the diagonal, these two, you just flip those, right? The two entries normally here, that's taken up there. The one entry is normally here, that's taken down there. You just flip those two along the diagonal. And the other two entries, those stay in their place. So here's A12, here's A21, those stay where they are, but you'll add a minus sign. And that's the general formula for the inverse of a 2 by 2 matrix, which exists if this expression D is not 0. And remember that expression D, because we will revisit that in just a few days. That is something that can be defined for other matrices as well. So we've seen an invertible 3 by 3 matrix. We've seen a general 2 by 2 matrix. Let's have one more example. And this time we'll choose a matrix that is not invertible, so that you can see what happens during the process if we start with a non-invertible A. Now, the A that I'm going to look at is a 3 by 3 A to make things a little more interesting again. And I'm going to use 1 to 1, minus 1 to 0, and 1, 6, 2. It's not clear, at least not to me at this moment, if that is an invertible matrix or not. So we just have to go through the motions. We'll start by putting this matrix on the left of a tableau, the identity on the right, and then let's do Gaussian elimination. We'll start with this as a first pivot element, and we'll try to zero out the column below this pivot element, and we can do this by adding the first row to the second and subtracting the first row from the third. That yields, well, the first row is not changed, so just copy that, including the right-hand sides. For the second row, we get minus 1 plus 1, that's 0. 2 plus 2, that's 4, and 0 plus 1 is 1. And on the right-hand side, we get 0 plus 1, 1 plus 0, and 0 plus 0. So 1, 1, 0. For the last row, we get, here we have 1 minus 1, that's 0. 6 minus 2 is 4. And 1 minus 1 is 1. 2 minus 1 is 1. And on the right-hand side, we get 0 minus 1, 0, and 1. So you can see here we have our first pivot here. And the second pivot is going to be this entry here, the 4. So to obtain zeros below that 4 here, we are just going to subtract the second row from the third one. And that yields 1, 2, 1, 1, 0, 0, 0, 4, 1, 1, 1, 0, and 4 minus 4 is 0, and 1 minus 1 is 0. And here we will get minus 2, minus 1, and 1. But what we can see right now is we now have echelon form on the left. And we can see there is a 0 row. So we only have 2 pivots for a 3 by 3 matrix. That means the rank of A is 2, and that's not 3. And that tells us the matrix A is non-invertible. And that also means we can stop right here, and we have to stop right here, because there's no way we could get this matrix here into the the form of an identity matrix. We will not get rid of the entries that we need to. So this concludes the examples. You've seen an example of how to compute an inverse matrix, of how to determine that a matrix is actually not invertible, and you've seen a general example and a formula for 2x2 matrices. There's going to be lots more examples on the exercise sheets as usual, so you will have an opportunity to practice a little more. And after you did so, we'll dig a little deeper into the theory of matrices. I hinted already at this mysterious D, and that's basically the next thing that we're going to look into. That D is also called the determinant, and that will be the topic of some of the next videos. I hope I'll see you then.